Started. Welcome, and I'm really happy to have Peter Grant here today. He's going to talk about green radio towards sustainable wireless networks, and given our history of work in the area of radio resource management here at WINLAB. So we're all really curious to find out, sort of what the various issues and challenges are. And Peter is a professor at the University of Edinburgh, and he actually holds 3 doctorates, a couple of them given to him for free. And he has won many awards, recognitions for his work throughout his career. And I thought there was one thing that he had down here that was very interesting. He's what is called as the Regis Professor. Right? I'm just reading directly from his file here. It says, regal chair appointments are conferred by the Queen of Great Britain. And in brackets, in parentheses, it says, as a title only without any financial support. So that is, we don't have the Queen, but we're sort of familiar with titles without financial support. So anyway, welcome, and we're happy to hear you.
Thank you very much for a very nice introduction.
I think you need to...
Okay, well, I'm going to talk a bit today about some work that's conducted in Britain through the mobile PCE. As my talk progresses, I'll explain a bit more about what mobile PCE is. But the mobile PCE is a collaboration between industry and the universities. It's funding work in the universities, and it funds work for 3 years at a time. So this is the Core 5 programme. So we've already had 12 years of work before this. And this is a presentation that I've put together. It was partly written by Simon Fletcher of NEC, and I've been helped from a couple of colleagues also to put this together. So I'm going to split my talk into 2 parts. I'm going to give you sort of the industry case for why we need green radio as the first part of the talk. And the second part of the talk is going to be, I'm going to talk you through the research program that we've just started. And that's the sort of format for this talk. And in the first part, I cannot get all the slides to completely match together. The facts that I give you are all slightly different because they're taken from different parts of the industry. So you have to bear with me on that. But I want to do that because that sort of illustrates and gives you the case for green radio. So why is green radio important? Well, energy costs are continuing to increase. And with more base stations, the energy cost goes up. And a typical UK mobile network might consume something of the order of 40 megawatts. And overall, this is quite a small percentage of our energy consumption, but there's a huge potential to save energy in other industries. So by having mobile, other industries like transport can hopefully be much more efficient. But also, we also have to look at the energy cost because great availability limits installation of base stations in emerging markets. And if you have to put in diesel generators, they're all quite expensive. And the other thing is, companies in Europe have a corporate responsibility to reduce their CO2. All companies have in their annual reports indications of reduced CO2. Vodafone, for example, have a group target to reduce their CO2 emissions by 50% between 2006 and 2020. And Orange, they're going to reduce the greenhouse emissions per customer by 20% between 2006 and 2020. So companies have to do that, and these are some of the companies that have contributed towards this slide set. So then we have to start with, where is the energy used? And if you look at this Vodafone figure down the bottom, you see the radio base station takes 57% of the energy. This is the mobile, he's running about 20%, and then you've got the data center, the core, and the retail for the rest of the energy. And so, and in the base station, if you look at this other diagram on the right here, this is actually tells you in the base station that embodied energy is the energy involved in building the base station, and the rest is the CO2 emissions that you would get per user per year. So in the base station, we have the energy in building or constructing or designing and fabricating the base station is quite small, but the operational energy is very large. And then if you look at the mobile handset, if we look at for one subscriber, that's quite different. Because the mobile handset is very, very sophisticated. There's an awful lot of energy goes into making the chips and designing the mobile handset and fabricating the mobile handset. And the battery power that the mobile handset uses per subscriber is really quite small. So the industry feels that we should be looking at actually at the base station because that's where most of the energy is actually being used or dissipated. So here's a slide from Vodafone. This is from their corporate review, 2007-2008. And this is how they've moved forward. This is the radio base station. This is the energy use in gigawatt hours. This is the rest of the network is in black. The office costs are in white, and the retail costs are in green. And this shows how the Vodafone consumption has moved forward 2004, 2005, 2006, 2007. And so there's been, you can say there's been a slight reduction over that period, but Vodafone feels that they need to do more. They need to try and do more, and particularly cutting down this green segment, which is the energy that's actually used within the base station.
So a question, Peter.
Yeah.
So do these energy use figures scale with the population served by the system, or with the area covered by the system?
Well, they would do, because this is what a UK operator like Vodafone would use for the GSM and plus the 3G network.
You got an operator with twice as many subscribers.
Then
the energy costs double?
The energy costs would go much larger, yes. Yeah, we'd expect them to more or less double. Because it would depend exactly how many base stations they had, how many base stations they deployed.
Right. So, for instance, an operator who covers rural areas, does he have higher energy costs per user because he's putting out signals and amplifiers in a lot of energy places?
Well, that's right. I mean, that's an issue because the rural cells are going to be larger in diameter, and therefore they're going to need more power to communicate to the users.
Right. So it's very hard to get a sense of how these things really work. Anyway.
Okay.
And also this reduction that you show here, right, from 2004 to 2007. So what is that attributed to? Have they done something better in terms of how?
Well, they're progressively trying to make the base stations more efficient. So they'll be making small changes in the base station efficiency. So that if they have to roll out more base stations to increase the size of the network, then they have been making some improvements in the overall efficiency. They've been procuring from the vendors, more efficient base station designs.
That's one IC generation, so you're going to buy some power saving.
I see. So okay, it's directly related to that.
This is 4 years.
Yeah.
Cycles to get some.
These energy costs are due to the operating costs or due to the power amplifier and the.
Well, let me come on to that. This is the total electricity that they use going into all their base stations for a network. And this is the base station cost. This is the rest. This is the backhaul and the rest of the network. This is what it would actually cost to put power into all offices that they have. The commercial offices in all the different towns. So it gives you an idea. So that's retail, and then the last is retail. Offices would be the offices of Vodafone itself, and then the retail segment would be the retail shops.
And how does a number like this compare, say, to a typical data center?
It's lower than a data center. We believe this is quite a bit lower than. Is it lower than a data center?
Because at least the green computing people all seem to talk about data centers, right?
Yes.
And so they talk about how they need sort of green computing.
I'd have to take that offline and go and work out. I haven't actually personally worked out what the consumption of a data center is. Because this is a network. This is a network for a population of like 60 million, of whom roughly half have cell phones.
This is annual, right?
Yeah, this is annual, yes.
Sorry, one last question. So basically, you want to reduce the energy consumption because of the cost, or
two things.
Or because of the CO2.
They want to reduce energy costs to reduce their operating expenditure, and at the same time they meet CO2 targets. So it's a bit of both.
So in terms of operating expenses, is it if you want to consider the whole cellular network, how much percentage? I don't know if you showed the graph. Is this very significant percentage of your operating costs, or
I can't tell you exactly what the base station electricity cost is with regard to the whole operating cost. I don't have that figure.
but if it's very less, why do you even bother about
CO2.
Well, you
CO2 is fine. CO2 is fine. I'm not sure about it.
it's CO2 and cost of operating the network. It's a bit of both. So if we go back to the previous pie chart, this is what the power consumption is. So this 57% is in the base station, 20% is in the switching, something like 15% is in the core network. The data center for the wireless, for your wireless system is only about 6 or 7%, and the retail is less than 5%. That's just a repeat, essentially, of the previous pie chart. Now, this is a slide on base station power use. It's taken from a German paper, and it goes back to 2003, because we can't find anything at the moment that's more up to date on this. And in this one, if you look at this, the transmit power that's quoted here is about 3%. So this is saying that the overall base station is about 3% efficient. Now, I'm not totally happy with that, but that's the slide we have. And if you look at that, then the power amplifier is 22%, the transceiver idling is 19%, the power supplies themselves are taking 6% of the overall power, the cooling fans are running at 13%, etc. So this is a paper from Technical University of Berlin in 2000, published in 2003, when they looked at the overall efficiency of the base station. But I think the base stations have improved significantly since then. And the slides that I'm showing you here, we've actually had to increase the efficiency number on the base station. But I come later on to talk about that. Then we've recently increased that because they are becoming more efficient, partly with the new design of ICs, but partly people are starting to address this. So if you want to look, here's a Nokia Siemens Networks slide. They say that currently, the now order possible on the currently, a GSM base station takes about 800 watts, and the wideband CDMA station takes about 500 watts. So that is the electrical load to run these base stations. A GSM one has a transmit power of something of the order of 100 watts. I think the wideband CDMA has an output power of about 40 watts. And the target to 2010 is to get the Nokia Siemens Networks wants to get this GSM one down to 650 watts, and the wideband CDMA down to 300 watts. So they want to try. The target is to make them more efficient and move them towards this sort of level. So the thing is about the energy consumption that the industry feels that the base station is the most energy-intensive component of a 3G mobile network. A typical 3G base station, as I said, is 500 watts with an output power of about 40 watts. This makes its average energy consumption of a base station about 4.5 megawatt hours. And remember, that is lower than a GSM base station, because the GSM base station would be taking more than that. So if you look at a network, if you were to look at a 3G mobile network with 12,000 base stations, that would consume over 50 gigawatt hours each year. And so this is, as we were talking just now, it's responsible for a large amount of CO2 emission, and also it contributes to the operating expenditure of the mobile operator. And to give you a feel for this, I mean, if you compare this in the UK with the broadcast television network, the broadcast television is much higher output powers, because you're talking about maybe tens or 100 kilowatts is the output. Then this network here is 10 times the consumption of a TV network. To try and put that into perspective. And of course, this number is going to be much worse if you go to the like of China, where there's 10 to 20 times the number of mobile subscribers that we have in the UK. Yeah.
The broadcast TV network is working 24 hours?
Yes. Almost 24 hours. I think it may be switched off between about sort of 2 o'clock and 5 o'clock in the morning, but then some channels keep going.
So what if you switch off the base stations from 2 o'clock, 5 o'clock, and how much do you say?
Yeah, well, that's an issue in the future. Is can we design them to have a sleep mode so that they get some reduction in power? Because some people will still be using the network between 2 and 5.
So we can allow for that optic switch, but basically you'll get 99%.
Yeah, but at the present moment they don't power them down. They run at full power all the time. So up till now nobody's thought about sleep modes in the base stations or low power modes in the base stations. This is something I've come across since I'm here actually, since I'm at Princeton for 6 weeks, is that if you look at a Wi-Fi laptop, then it's not the laptop, the Wi-Fi part of your laptop is only something like 1 to 2% efficient when you compare the radiated power against the total power that you have to put into the laptop. So I just mentioned that in passing. So what's the challenge? Well, the real challenge is driven partly by the growth of data on the mobile networks. And at the present moment, we think mobile networks are growing about 400% per annum. And I read 2 weeks ago in the New York Times that AT&T had got 40% additional revenue from selling iPhones. So the iPhones had increased the revenue to AT&T, but the downside was that quite a few of their base stations and their cells are now saturated with traffic because it's much more data traffic. And so if we didn't do anything else about this, the data traffic, it would be a higher energy consumption to take account of that. So we have to design future mobile networks that are going to be more efficient to allow for this growth in traffic. And what we're actually seeing is that as we move from voice to data, that the traffic is actually getting an exponential growth, but the revenue is not following that growth curve. And that's partly because people are pricing data in fixed bundles. So if you move to having your laptop and plugging in a dongle and then having wireless access through the 3G network, then as you download, you're putting a lot more stress on that network than it would be for voice calls, and you're not having to pay for that at the same level as you're paying for voice calls. So we've got this divergence between the traffic and the revenue, and we would obviously, to support this traffic, we will need more base stations. And that's going to cause increase in the size of the network. So that's one of the issues. Another issue as to why we've got to be more efficient. So the energy use cannot follow the traffic growth without a significant increase in energy consumption. So we have to work towards reducing the energy we use per data bit carried. We see the number of base stations increasing, so we must somehow get down to reducing the operating power per cell. And that's one of the reasons why we are particularly keen to look at green radio research. Now, yep.
Since you're doing the business numbers on that, if I look at a base station and I do its current costs based on operation plus capital to buy it, plus the siting costs, where does the energy fit into that? If I'm going to increase base, I'm going to double the number of base stations. Is it mostly capital and finding church towers to put it on, or is it electrical usage?
I can't actually, since I don't work for a mobile company, I can't actually answer that question accurately for you. We could go in and think about that, but I can't give you an immediate answer to that today.
I suspect the cell site towers will cost more than the electricity.
Then the what?
Than the electricity and the
No,
power.
that's thoughts. I agree, but it's, if you have to incubate over what time?
You have to integrate over 5 years.
At least. And then once you have the tower, or you put it somewhere, you're not going to pay for that ever again.
No, okay, I'm just talking about
It's still possible.
base stations.
No, I agree.
Yeah.
I'm just saying, I mean, if it's $200,000 a year
I'm just talking about the
for
capex,
electricity,
not about
that very quickly reaches $2 million for the
I'm
site.
just talking about the capex, for example, the power amplifier cost as against the cell site. Not the.
Electronics cost is zero compared to the actual base station costs $75,000.
I think like the network piece site is 40 megawatts corresponds to a cost of energy about equal to 200 employees for a year. 40 megawatts, that's about $4,000 an hour. You hire a place for $20 an hour. So it's 200 employees.
For the whole network.
Yeah.
Right.
So if you're running a network like that, a nationwide network with a couple thousand employees,
It's a significant number.
Huh?
It's a significant number.
Yeah, it's not trivial, right? But on the other hand, if you're employing 20,000 people, it's kind of small.
Okay, well, the way we're addressing this is in the mobile PC, which is an industry university collaboration, then we have a visions group, and the visions group go away and think about this. These slides essentially come from material that the visions group has put together, and they are really saying that we need to try and achieve something of 2 to 3 orders of magnitude lower power transmission. If that really should be the goal. And they don't see that coming necessarily from standard research on the physical layer. They think we need, if you look in red, they believe we need a holistic system-wide breakthrough thinking that challenges some of our current basic assumptions. And this is what we're trying to do, and we're trying to take forward existing research. And our aim is to try and make a significant difference in this field. And I'll talk about some of the research directions that we're thinking about moving in later.
Thanks, one more.
Yeah.
I met many years ago with the Swiss regulatory agency that deals with their FCC, or I forget what it's called. And one of the issues, apparently, at least in Switzerland, was people were really worried about visible radiators and radiation exposure.
Uh-huh.
And the question is, at what level does that affect? You're talking about lowering the overall network radiation by 2 orders of magnitude. Do those regulatory issues fit in there too, or the popular perception issues, or is that faded away over the years?
No, that's not faded away, because when you install a base station in a church steeple, there's normally a public meeting, and you get all sorts of comments around that. But what the public don't realise is that even if a base station is putting out 100 watts, there's much more problem by having a handset close to your head if you're in a cell.
The question is, how does it fit into the popular perception?
I don't know how you get that information over to the public, which is not to make a long call if you're at cell edge and the power level on the signal level on your phone is low, because that's going to do much more damage to you. So people have the view, and people say that they can't sleep because they need to live in a Faraday cage if they live within a certain distance from a base station.
But they click on their Bluetooth.
Yes, yeah, but they don't. The public doesn't think about that. That's public perception. I've been shouted down at church meetings in Edinburgh, I should tell you on this.
Do you think these advancements are going to come in the electronic technology or the communication, the transmission technology?
I think we've got to look at both. We've got to look a bit about the electronics, the power amplifiers. I'll come on to that in a moment. But we've also got to look about how we configure the system and how we run the system. And there are other clever ways of doing it. So we need to look a bit about both, and I'll come to that. So we're particularly interested in green radio, and some of the things that we want to think about or look about is maybe looking at using some information we have about the mobile, and I'll come back to this. Can we take information about the location, speed, and direction to improve the operation of the system? And I'll show you some of the thinking on that in a moment. Some characteristics of the multimedia traffic, for example, how much can we delay traffic? You obviously can't delay a telephone call, but you can delay a download. And if by delaying the download for a reasonable length of time, you can get a better power consumption, a lower power consumption, then that's a way forward. And we want to look at transmission power scaling, because we also need to get it down, because we need to think about base stations that use renewable energy. Because if we also think about a developed world, then everything can't be powered off the grid. And so that is another area that we want to be addressing and thinking about. So here are some of the scenarios. In the developed world, we've got a developed infrastructure, we're largely into saturated markets. Quality of service is the key issue, and the drive here really is to reduce cost, because it's partly to maintain competitiveness against other network suppliers. So cost is seen mainly as a driver industry sees cost as a driver here in the developed world. But if we go to emerging markets, there's less established infrastructure. We've often got to cover large geographical areas, and often there's no mains power supply. So power consumption is also a significant issue there. And so we essentially have these two markets, and actually the data center people have different designs of data centers. For example, in India and here in the US, and that's just because of the differences in these different markets. So we need to think about both of these activities.
And if you talk about cost as a driver, to what extent is data a driver? That's sort of the quality of service, but it's slightly different. To what extent do you expect the higher data rates to be a driver?
Well, I think that higher data rates are a driver because because we're providing higher data rates for essentially a fixed price, which is much lower than the price for speech and text messages. Speech and text messages, people are paying quite a high price to use the network. In comparison, the price on data is much lower. In Britain, if you buy a dongle to plug into your computer, you're paying about $15 for a gigabyte of download, and then you pay about another $15 when you upgrade to get the next gigabyte. I mean that is the current sort of price for Three and Vodafone, and more people are thinking about doing that. So they're not just using their iPhones and their Blackberries; they want to use their laptops over the network. And that is going to make a vast increase in the data. And that's what's driving the 400% per annum increase in data traffic. And I think that's, I think that's going to be, they're going to allow that because they're selling that, but I don't think that Opera have necessarily thought all the way through about what effect that has on the network in terms of, that's my personal view.
Well, Twitter gets.
So if you look at solar energy, we think a 1 meter squared solar panel would produce about 400 kilowatt hours of energy. It would be about 10% of the requirement for a 3G base station. But if that was in London, because of the less sun that they have in London, they'll keep here, that would only provide about 5% of a base station. So there's going to be quite a difference between what you would get out of a meter squared of solar panels and what you require to run a current base station. And I heard a statement, and I've never actually checked it, was one of my colleagues many years ago told me, you'll never recover the body of the manufacturing energy that it takes to make a solar cell. So the output from a solar cell will not recover the amount of energy that's involved in its manufacture. I don't know if that fact is still true. But we think a combination of solar and wind sources in an appropriate location might be able to provide the energy requirement for a small femto or picocell base station. So we think that there's a possibility of using renewables for that. So with that as the background, that's the industry view. That's the industry view of where we are and where we're going and what the issues are. So we have this collaboration in Britain. Let me take a moment or two to explain to you. It's the mobile PC. Industry pays a subscription. Companies pay $60,000 a year, or if they're really generous like Vodafone, and pay a double subscription. 20 of these companies, we take all that money together for 20 of these companies, and then the British government provides us research funding that more or less matches that money or gives us more money than that. And then that goes down into a set of universities. It's not just one university, but it's now currently 10 universities. As we're moving forward 2009 to 2012, we have 3 distinct programs. We have Green Radio, I'm talking about today. There's also, we have funded user interaction or the user interface at a lower level. We're actually looking at the user interface, and we're also looking at flexible networks. And flexible networks is partly funded, and we're going to try and get a second round of funding on that. So this essentially is it's industry driven, but it's university delivered. The way it works is the companies pay their $60,000 a year subscriptions. We put that into the vendors fund. That gets matched or more by the government. Typically, the equivalent of NSF in the UK is EPSRC, the Engineering and Physical Sciences Research Council. We have a strategic partnership with the Research Council, so they max money or give us more money. That gives us the core program funding, and then that goes down into the universities for it to be delivered. And the universities have had to compete this time. Up till now, the universities were fixed. It wasn't changing. Edinburgh was not in at the very beginning. In 1996, Edinburgh with Southampton joined as an associate member, but we've been quite heavily involved, and we've moved up to full member. And I actually, at the moment, sit on the board. I'm a company director for 3 years of the mobile VC. So that's the model. And then industry monitors the program. So in Green Radio, this is how Green Radio is organised. The chairman is Simon Fletcher from NEC in the UK. Andy Jeffries was the chairman until Nortel went into Chapter 11 bankruptcy, and he's moved to being associate. We hope he carries on as with us. And David Lister from Vodafone is one of the other people. These are the companies that are funding the mobile VC that are particularly interested in Green Radio. And therefore, these are the companies that want to come to the quarterly meetings and listen to what the researchers are doing. And then they basically, we discuss with industry what the techniques we want to develop. They tell us yes, no, and then we write a proposal based on what they say is yes. I could be interested in you. And the companies can work together because this is pre-competitive work. Research is going quite a long way out. So there's no difficulty about Orange actually working together with Vodafone on this. Because we're actually looking at far out research, and then we submit patents, mobile VC pays for them, and then the companies have a royalty-free right to use them because they fund the universities at what is called full economic costs. This is the academic team on Green Radio. The academic coordinates a colleague of mine in Edinburgh, Steve McLaughlin, and also we're involving this work from Swansea, work from Bristol, and work from King's College. So there are 4 universities that are collaborating here. There's normally a professor, and there's some lecturers or readers within universities, and then they have, here's the supervisors, then they have below that the postdocs and the PhD students who are actually delivering the program. So these are the objectives that we've sort of set ourselves. We need to make the base station more efficient. So the power amplifier, can we do more on the DSP? Can we introduce sleep modes? We need to look at the backhaul, because we need to look at the power consumption within the backhaul. And then we also want, at the same time, to look at the overall system operation. So we need to we want to really start analysing whether we can use multi-hop routing, whether we can use relaying, how can we improve the spectral resource allocation, and we're thinking of using some DSA also within these designs. So that's sort of a helicopter view from the top of what we're trying to do in this research program that we're just starting. So the way we've organised it is, I talked about the industry steering group. I'll come back and talk about the energy focus group. We've divided our research into 2 areas. One area we call architecture, and the other area we call techniques. So architecture has got 7 people working on it, and techniques is going to have 9 people working on it. And the idea in architecture is to try and identify a green network architecture, low power wireless network and backhaul that still provides acceptable quality of service. And the techniques people are going to identify some of the base radio techniques across all layers of the protocol stack that can achieve, the goal is to get 100% power reduction. So the industry has set us this goal. I'm not sure we're going to achieve 100% power reduction, but that's the overall goal. And these 2 technical work areas have underneath them 48 man-years of effort, because postdocs are employed for 2.5 years, PhDs are with us for 3 years in the UK system. So now let's go, first of all, let's dig down a bit in architecture, and then let's dig down a bit in techniques. So these are what we're currently proposing to do within architecture. We have to establish the baselines. We need a clear understanding of the energy consumption in current networks and the network elements, the base stations, the mobiles. And this scenario is defined in what we call the book of assumptions. So industry works comes up with this book of assumptions for us, and we use that as our benchmark or our baseline. And then we need to also look at the backhaul strategy for a given architecture, because we can't change the architecture without also giving some consideration to the backhaul. And we want to look at the development scenarios, what's the optimum deployment scenarios that will give wide area network given a clearly defined energy efficiency metric. So this is what we're trying to do in our architecture. The technical approach we're adopting is deriving these energy metrics to accurately quantify consumption. The communications network energy consumption models for the radio access, we need to understand that properly. Then we need to look at radio access network technology. We need to look at different cell sizes. Do we do one big cell or do we do many smaller cells? We need to assess whether we can put in relay nodes, as I'll mention to you in a moment. And we need to look at the backhaul. We also want to look at multi-hop routing, because so far we haven't used multi-hop routing in cellular systems. And what would be the energy benefit in installing multi-hop routings by a strict end-to-end quality of service? And we need to look at if there's delay, if we can use mobility in some way to delay transmissions and therefore save power. And we also need to look at frequency management, try to identify energy efficient physical layer architectures. On that, we want to, as I mentioned, use DSA to see if we can minimize the energy consumption by utilizing bands with particularly low interference. And we do need to look at solar powered relaying, allocating resources to match the traffic and with any weather patterns. So in terms of cell size, I mean, do we go for a big macro cell, or do we go down to microcells, picocells, and femtocells? And we haven't so far performed an efficiency analysis across the different sizes of cells. Obviously, as the cell size reduces, the power consumption goes down on the base station. But on the other hand, you need more base stations to cover the area. So we need to do this trade-off against large and small cells. We need to look at the source and network coding and cooperative networking. And we need to evaluate the optimum cell size for these different perspectives: radio resource management, greater frame error rate against NSDB over N naught. We need to look into the link budget, and we need to look at mobility and traffic models. So we intend to do essentially an efficiency analysis when looking at different configurations for different cell sizes, and that's part of the research work that we need to conduct.
So, yeah, I have a question. So, have people sort of thought about, or at least have they sort of had any ideas about how you can relate power consumption or reduction in power consumption to reduction in carbon offsets? I mean, initially you had some numbers, right? You were saying that the base station had so much carbon offsets. You had some numbers. But suppose that, let's say I had a 3 dB improvement in my base station transfer power.
Yep.
How does that translate to making me more green, so to speak?
Well, because then if your power for the mains goes down per base station, then you get that reduction in your power you use to operate your network.
Right, I see that, but I'm saying in terms of, if you look at it as a whole system, is that 3 dB power translate to something significant in terms of something like a carbon offset, or is it?
Well, it's I mean, the companies want to try and make sure that they can have a green label which says that they're using less energy next year to what they're using this year, and then they're progressively trying to move down, while they've got to handle more data traffic. And so that it just links, I understand it just links to the power you use. Your CO2 emission is directly linked to the power you consume.
Is the approach on the energy matrix in the vehicle all going up or unified to the same energy matrix, or there are different perspectives?
Can you explain what you mean by energy matrix?
Yeah, you just proposed?
I think the metrics would.
Oh, metric. Well, we're working from, we've been given a book of assumptions that we can use as our baseline, and then we've got to try and see if we can potentially design systems that can improve upon that.
So is this in the public domain? I mean,
No, that's not entirely the public domain, because that's within this program. So that's behind the firewall and the yes. Because industry has given us that as a starting point. So we don't. I'm afraid we don't have that in the public domain.
The program unified definition for the energy matrix?
No, because it's continuously changing. As there's not. And that's the companies have to discuss with each other, and then they agree with us. They give that as a starting point.
Why?
Why?
Yeah, why people need changing the definition of energy matrix? Because that a couple of groups, people from our groups, they said that some proposals, but the difficulty is that we cannot improve our definition of energy matrix. We propose different versions of this definition, but we cannot achieve like agreement. So I'm just wondering why. What's the reason why people cannot?
Well, our industry's got together and defined for us what they think the baseline is. So they have managed to come up for us with a base, because we need a baseline definition to work from. If we have companies are very secretive about what their individual networks consume. But we've managed to get an open discussion as a starter for that. We worked many years ago with Nortel Networks, and they did a whole lot of propagation trials and worked out what was the channel characteristics, but they would never give us access to that. Because in British talk they called that the crown jewels. And they said it's far too valuable for us to make that available openly. And so we discussed with them what we would use as typical channels for doing MIMO simulations. And then they would just sit and say, yes, that's all right, you can use that. But they wouldn't give us access to the actual propagation data. They asked us to come up with our own models, and then we had to discuss with them as to whether they were happy or not. And they said, no, these are not sophisticated enough models. You've got the wrong range of delay or the wrong range of angle. And so we had to work with them, but they would never actually give us their data. And that's just because of the way companies behave. Yeah.
It seems like this progression from macro to femto has the effect that an operator like Vodafone will be able to offload their energy consumption on someone else. Femto is a local user access point object that's plugged into your house. Suddenly, what was their energy cost is now
it becomes somebody else's energy cost.
Right. And so you end up getting an outcome maybe where it's in Vodafone's interest to get there, right? But on a national perspective, everything's a little worse, right?
But I think we must take it into account. We mustn't just assume that. I mean, that's now you're talking about in the house.
I'm not saying that is the way it is. I'm saying that's a possibility.
We're trying to make sure we don't do that, because we're thinking of the femto cells as being infrastructure that the cell phone company puts up. We're not.
It's a tricky calculation in some sense, right? Because actually, maybe the femto cell is reusing in terms of data infrastructure, right? Maybe it's reusing an internet access through a cable modem or something that would already be there anyway. So this kind of marginal consumption is kind of a tricky thing. So I'd be quite curious to see how it's progressing.
So eventually the research will be public domain, or?
Yes, the research will be published in the public. What happens is the research is published in the public domain. The papers are approved by a technical steering group, and certain amount of it is up, and stuff is patented. So at present moment, we've got a portfolio for the last 12 years of something like 45 patents. We're gradually not necessarily keeping all of them. Ones that we think have got less commercial value are dropping off. But these patents are there for the industry to use. So people that are funding the mobile VC can use these patents because that's part of the deal, and we can also sell or license the patents to other people that are not partners in the mobile VC. But the academics are not committed. After it has been patented and the intellectual property has been covered, then we're able to publish openly in conferences and journals. So here's some of the sort of examples that we might be thinking about. The first one actually is this is hydrodynamics figure. The first one is using the information about how a mobile is moving. So rather than necessarily transmit to the mobile when he's far out, which requires quite a high power level, why don't we wait until the mobile comes closer into range, and then we need less transmit power in the base station. So that's something that we want to investigate. We haven't really thought about that before, but the companies are interested in looking at that. Well, the other thing is what you were talking about was the relay. So here's the relay within the building, but the relay using exactly the same standard that we have. So it's taking the transmissions and it's allowing us to cover inside the building without needing a significantly high power for the base station to allow for propagation through the walls of the building. So we need to analyse that and see whether in-building relaying will give us a benefit. And then the other type of relaying is fixed relays and mobile relays, and also then as mobiles move, then we can actually and come within range. Then we can have multi-hop. I mean, we haven't really thought about trying to incorporate this into cell phone systems. We think about this in wireless sensor networks, but we're not thinking that much about cell phone systems. And the fourth approach would be to change system. Would be to move from a cell phone system to a wireless LAN system. So we have a relay, but the relay is operating on a different standard. I think I should mention. And so that's another way, but still delivering the data traffic or the voice traffic down to other users. So these are all these introduce delay. But can we use some of these techniques? Can we realistically think of using some of these techniques and actually essentially get a reduction in the power we require at the base station, and that will, the 3 dBs will come down to a reduction in the overall power consumption that we need to operate the network. So we go to smaller cells, but we need more of them. But this is another way of trying to actually improve the performance of the system in terms of energy use. And in architecture, this is how we're doing it. We're going to look first of all at some of the key metrics and establish the metrics from the book of assumptions. That's a 9-month task, and all researchers are participating in it. It's what we're doing at the moment. Hope to finish this about September, October time, and then we'll get a selection of key metrics on where we think we are and where we think we should be going. Then we're going to go into 3 different areas. We're going to look at energy efficient architectures. I think we'll devote 8 to 9 man-years to that. We want to look at multi-hop, and we think that's probably about 6 man-years of effort. And we want to look a bit about frequency management, and we think frequency management will probably be about 4 man-years. And so, yep.
If CO2 perspective, is the goal to reduce energy consumption of the cellular companies, or is the goal to reduce the overall energy of the country?
No, it's the cellular companies that are interested in reducing their consumption.
So if you offload the energy use onto other users like Coil putting out, then the CO2 consumption of the country or the world as a whole doesn't.
That change. No. The idea is we don't want to. We have to keep counting that if we use different. If we use a relay with a different route, we still want to count that as part of the overall energy consumption of the operator. So the idea is to get the operator's energy consumption down so that there's a reduction in the energy consumption within the country.
That doesn't necessarily follow, right? Because you're now offloading the energy cost onto, let's say, a relay or like in the diagram.
Yeah.
No, he just did accounting.
We have to account for that as system costs. We have to keep counting that. That's part of the cost of delivering the bits out to the remote parts of the network. And then there's these other tasks down below. that performs overall architecture assessment, and then these ones down below, 3 and 4, will address more specific issues. So within the architecture part, we've got the front part is like the first 9 months, and then we're going to split up and look at architectures, multi-hop, and frequency management. So that's how we plan that. Now the other part of the program is techniques. So we've got, as I mentioned at the beginning, we've got slightly more people employed on techniques. So we need to look at overall base station efficiency as measured as the RF output power to the total input power. So what we need to try and do is reduce the required RF power required from the base station in the developed world while maintaining the required quality of service. So we're particularly interested here in maintaining a quality of service. And given a base station nominal energy requirement, and then this is the 2.4 kilowatts times 100, with 100 watts times the 24 hours, we need to decide how this can be best used for communication. So we're actually using the energy in an optimum way. And also we need to think about sleep mechanisms. At the present moment, we're not incorporating any sleep mechanisms in the base station, but they could potentially deliver substantial reductions in power consumption if the load is low. And so we need to develop techniques that allow us to scale the power use with the load in the communication system. So this is what we're trying to do. And so we need, at the present moment, the latest update on this slide as I left the company was, people are now talking about 12% as a base station overall efficiency, if you measure RF power output to total power input. Now these all take different, these parts in here all have different total percentage effects within a base station, but these are the individual efficiencies in climate control, the power supply, and the power amplifier, the transceiver, and the feeder cables. And so we need to be looking at all these different elements of a base station to see if it's not possible to increase the overall efficiency. And although the very first, the pie chart that I showed you from Germany from 2002, and it was saying it was 3% efficient, at the present moment, current base station designs are about, overall efficiency is about 12%. So we need to look at advanced architectures, multi-mode and multi-standard, and we need to try and maximise the equipment in the base station reuse. And we also need to look at integration, which allows energy reduction. So we should probably be moving more of the electronics up the masthead, and the target would be to get an overall efficiency up to more than 20% improvement in overall efficiency. And also we need to look at the power amplifiers themselves. The power amplifiers, the transceivers are currently, the base ones are only about 45% efficient, and the target is to get that up to 60%. And we're thinking of doing that by an envelope tracking method. And the thing is about the masthead is the masthead power amplifier gets rid of the feeder losses, the integration avoids the interconnection losses, and actually we might in Britain there might be quite a bit of thermal cooling when the weather's colder. So it may be, we need to look at that, and we need to look at that for building base stations in different areas as to whether we can actually put more of the electronics up by the antenna and avoid the Texas bullets. Yes.
So if you're putting relays, what kind of relays are you thinking about? So those relays are also going to consume power and
yes. So we have to take
going to offset the.
Well, we have to do the calculation of what's the total power consumed with the relay's mains powered or the battery powered. We must keep track of that within our calculation.
So those things is it being decided, or it's just?
No, it's not. We want to do the research and see if the research says that we could think about installing this, incorporating this into real systems.
So none of this has been done yet.
No. I'm talking about a research program that we're starting to deliver.
Okay. So in fact, I was going to tell you, you've written a paper on green radio now. The stuff we did with Alcatel, with Ronaldo and Jerry.
Yeah, but we only looked at trans power.
Yeah, we looked only at transfer power, right?
So I guess to redo everything we've done before, look at total energy.
So I also looked at total energy.
Oh, you did?
I stand the paper.
Yeah, so maybe you should.
Yeah,
point your-
maybe
yeah.
check that through.
In several companies, UK has a mandate for government to, do they have an economical incentive for government to reduce their carbon?
All companies in Britain have to have a corporate plan that reduces their carbon footprint. Because if they don't have a corporate plan that reduces their carbon footprint, they will have a very difficult annual general meeting, because the public will demand it. So essentially, it's yeah, okay. Here in America, up till recently, you've been driven by the George Bush. CO2 emissions don't matter. Then you see you're changing as well, and so from the Kyoto Protocol in Europe, all the companies have to have a corporate plan for how they will reduce their CO2 emissions. And likewise, the power companies have got to have the same thing. So the power companies are working really hard on what's called, if it's a coal-fired power station, carbon capture the carbon and pump it into the ground. So everybody has to have CO2 reduction is talked about all the time. And that's the cell phone companies cannot avoid that. So that's why they put that. That's why Vodafone put these numbers in their corporate report. Then everybody feels happy that they've taken it on, that they will be making this reduction in CO2 emissions. The thing is, one of the things is obviously it's a big impact in transport, because if cellular networks allow transport to be more efficient, there's a follow-on carbon reduction in other industries, and that's quite difficult to quantify. If the trucks are more efficient in the delivery route and can reroute because of traffic delays, then you've actually, that's one example of how you get a knock-on effect in other industries. So DSP and radio resource management, people want to investigate this. Interference minimization and cancellation. Radio resource management techniques for trying to reduce the power consumption. And any other novel approaches in network coding, or can we take some techniques from sensor networks, cross-layer technologies that are very grounded in standards, and actually bring them into what we do in cell phone systems.
It's not clear to me how network coding is going to improve in power savings. Or is it just something which
It's not clear. That's why it's research.
That's
serious.
Network coding might allow us to pump down more data, and then the question is how much extra processing power will we need to implement the network coding? So then you've got a trade-off. You could do a trade-off of keeping the current system and putting double the number of going down a level, so doubling the base stations, or leaving the one big base station and employing network coding. So that we haven't thought about that, and we probably need to think about that.
it's not just because it's a buzzword and
No, it's not because no, it's not buzzword. What's happened is we've thrown out ideas to the industry, and all these companies have sat around with the people that are leading this, and they basically do tick and cross. And they said, no, we're funding most of it, we don't want you to work on that. But yes, that looks an interesting idea. So they're actually, it's essentially, I would describe it to you as an industry steered program. It's really more a university thought out program, but then it's steered from industry. So in techniques, we've got, just like the architectures, there's an investigation and evaluation phase to begin with. And that's like 9 months involving all researchers. Again, that should be finished in September, October. We want to identify some of the approaches that we think are going to be important. This is bringing everybody up to speed. And then we're going to look at the techniques for power reduction. And we're going to, that's a top-down systems perspective. And then we're going to look at resource management, probably put 7 man-years into that. 6 to 7 man-years to see if we can look at anything about making DSP more efficient, and about 5 man-years into the hardware, the power amplifier design, etc. So from the top level, this is how we're dividing the effort out essentially across the 4 universities over the three and a half years of this particular program. And then, so these actually are essentially addressing techniques across the protocol stack. how we work. And deliverables will be, year one will have a workshop to discuss the architecture, metrics and the promising techniques for power reduction. There'll then be an executive summary on energy and power efficiency in terms of metrics and trade-offs. Year two will have a poster day with some of our initial results, and then we'll produce some reports on the efficiency gain. And year three will have reports on the overall program achievements for both architecture and techniques work packages. And there'll be executive summaries of the key outputs from this particular program. So that's the overall way we look at it. And this is coordinated from industry, as I mentioned several times. So basically, the industry has a monthly coordinated steering group meeting, and this is basically mostly done by telephone. They don't actually always physically get together. There's quarterly technical steering group meetings where the researchers all come together, and they basically report on the results over the last quarter, and that's in detail. And that's when the companies can extract most value. It's by all these different, the sort of 12 to 15 companies that are involved. They have to send the right technical people to these steering group meetings, because that's when they can both understand where the person's at and how they can influence the future. Because things get driven in different directions as a result of the outputs that we have of these. And we have a well-established approach for Core 5 in terms of, we have to look at the synergies between green radio and networks, network coding, routing, adaptive and self-organization. We'll be using internet-based interaction between the researchers and industrialists. We'll be using a wiki. And we also have an industry energy focus group in terms of trying to work out how we're doing and whether we're having any effect. So industry has a focus group that's trying to relate what we've got to the real world metrics, the real world costs, the real world constraints, the real world system parameters, and basically they're feeding this back as our research comes out. They're feeding this back to us. Because what we're trying to do is get some sort of optimized, suggest what the optimized design should be on this metrics optimization graph. So the idea of this is it's tightly coupled to the architecture research. They will involve a set of targeted questions which they'll give us, which we'll have to go away and try and answer. And we'll do analysis abstraction for realistic industrial applications. And they will continuously work and see what are the energy metrics that we must use to ensure that our configurations and our research results are going to be ultimately be applicable in real cellular systems. And this is an example of the diary from where we are now. We had an education day at the end of April, to brief all the researchers on the industry state of the art. Now that all the people are on board, to bring them up to speed in this program. The next quarterly steering group is the 2nd of July. We're planning a metrics workshop on the 9th of September to review where we are, what are some of the techniques, and everybody will be come to that meeting. And then there'll be another industry steering group meeting on the 1st of October, because these occur quarterly. We also have global outreach into other events. We did a day at Orange in Paris just before the WWRF meeting, and we're also working with the Femto Forum. You know, we're supporting part of the Femto Forum Research Day in London, and we're having ongoing discussions with the Femto Forum. We're not tied into the Femto Forum, but we want to make sure that we understand what their 8 priorities and issues are, and we want to see whether any of that matches into our program. So these are some of the conclusions we've got. We're looking for these green technology relevant to business and politics. Green radio has to be driving our research. It's a 48-9-year program, as I've described to you. It's really important for the operators because they need to think green in their future networks. The public will not allow them to pass on that one. And we also need to, the equipment vendors need to try and find out what are some of the key techniques that can give them emerging green solutions. The other way to look at the program, that's sort of from a system standpoint, is to look at what we're trying to do. So we're trying to deliver benefit to the network operators via the equipment supply chain vendors, and we plan to research and investigate changes to the system architecture and to develop advanced networking techniques that will enable us to deliver in the future more efficient green radio systems. So I realise this is actually quite early in our programme, but there's been a lot of work that's gone towards this, and industry's worked very hard in terms of trying to define what should be our overall objectives, and try and help the universities to see which of the techniques that they really think they should be looking at and investigating, and which of the techniques industry feels collectively are not going to provide very much value, and therefore that are not worth investigating. Thank you.
So I didn't see much mention of renewable energy sources. I mean, is there something, are any of the universities sort of looking at that? Or,
Well, renewable energy is not something that we would investigate in this programme, because there's a very big programme in Britain called the Energy Technology Partnership, and a whole lot of companies have put up money, and the government's put up matching money, and they're looking at renewable energy or sustainable energy systems. And so that's really dealt with by the energy and power people, particularly electrical, mechanical, and chemical engineers for storage. So there are a whole other areas of people that are looking at that.
So, are cellular providers in the US also interested in this green radio concept?
Yeah.
You said Vodafone and Orange are interested.
Well, I think there's a growing interest in here, particularly because there's Princeton, WINLAB and Stevens have got a proposal in called FIRE. I've got a big program for it. there is a bit.
I've written a proposal on this. I thought I'd find out from Peter what it's all about.
Well, Vince is very is very reason that I come at this time, because Vince has a statement that he feels that Europe, particularly the mobile VC, is further down the road.
I made that statement.
You made that?
That's enough proposal. I just it's my contribution.
Good, thank you very much. I have to get that written on a piece of paper for the.
No, Vince said it.
So at the present moment, I think the feeling is that we're probably further ahead of than you here on thinking. But with the change in your administration, I think you're going to be getting more money and catching up on us very quite rapidly.
I believe it when we win the proposal.
Yeah, okay, well, I hope you will. And actually, this proposal has Edinburgh, we are a partner, and KTH are a partner, and INRI in France are a partner. So the idea is that if this proposal is funded, there will be some linkages. And actually, we are supported by a number of companies in the Far East, like Toshiba, Huawei. They actually pay into this program because they find value in collaborating this way. And it's set up it's called a VCE, which is Virtual Centre of Excellence, because it was identified a long time ago, like that there are pockets of expertise in Britain in each of the universities in communications. You can't put them all together into one university, into one centre, because the way the universities deliver teaching and research, you have to leave them. So that's why it's called a virtual centre of excellence, because they want to link together all these universities in a collaborative programme. So it's quite different, because we always used to compete with each other for funding. You know, you would try to think up the best proposals, and you got money instead of Princeton getting money, or MIT getting money. But we've been forced into. We're quite happy to do it this way, but we have much more collaboration between, and that's the way the industry wants, because industry wants to get the expertise from different universities to try and optimise the research achievements.
To your knowledge, is there any regulatory body like EPSR has taken any action to regulate the specification in green radio?
No, we don't. So far, we don't. The regulators haven't regulated on the power consumption. The regulator essentially only in Britain, the Radio Communications Agency regulates on the allocations, frequency allocations. There's a very interesting thing happening in Britain, because GSM started at 900 megs with Vodafone, and it used to be Cellnet, it used to be BT, and so it's actually Vodafone and there's two companies have the allocation at 900 megs. At 1.8 gigahertz, there's 4 cellular companies. But they want all the companies to have allocations at 900 megahertz. It's really important for rural systems because because you can get better propagation at the lower frequency, and therefore if you're trying to develop, and so they're trying to force. It's actually Vodafone and O2. They're trying to force Vodafone and O2 to give up some of their allocations, and that's the Radio Communications Agency. And the present moment, they can't get agreement from the companies to do that, and they're threatening to impose it on them if they can't get agreement. So that's what the regulator is really more a spectrum regulator, and he says what spectrum you can use and how you can use it.
Is there any overlapping between video and networking?
Well, I mean, yes, I think that will be an area, because if we go to dynamic spectrum access, then dynamic spectrum access and cognitive radio is one of the techniques we have in the toolkit, and I think we need to be investigating that. Yes.
So we also need to look at the national energy consumption in terms of for all cellular providers given together, because right now there are 4 providers, each one of them reduce their energy consumption, and then a 5th one comes up, and we are ultimately increasing the entire energy consumption of the country.
Yes. Mm-hmm.
So, should we put a cap on how much the country is supposed to use or emit?
As population increases, your energy consumption will increase. Right?
Yeah, energy per
But that's what these Kyoto, I don't know the details of it, but at least Kyoto protocols try to put caps on emissions, right? I mean, I don't know how they define it, but that's sort of the idea, right? And which is why the US didn't want any part of that, because they
Your President Bush didn't believe in it. But I think it is. Well, yes. So you see, Britain as a nation has got a target to achieve, and therefore the cell phone industry has to be included in that target, and so that's part of the driver.
So it's interesting. Is it based per capita or? Because I mean,
No,
it's related, right? I mean, if you have a cell phone, if you have in Antarctica,
Yes.
per capita consumption is 0. Actually,
Yeah.
there are no PlayStation, nobody's using cell phones, right? Whereas in New York City, it's probably huge
Yes. Mm-hmm.
because everybody has a cell phone. So it's an interesting.
The molecular metric itself is very interesting. If you say energy per bit, and then suddenly everybody stops loading, so the number of bits increases.
Yeah, or per capita. I mean,
Yeah.
should we be entitled to a certain number of minutes per day?
Well, would people be prepared to accept that? I don't think people would be prepared to
No, I
accept
agree. I'm just saying. It's an interesting how we define it.
Well, as I look at it, that, we have to look at energy consumption, because energy consumption linked to CO2 emissions. We've got to improve our CO2 emissions, so we've got to be more efficient. But also, I think the data explosion is a tremendous issue for mobile, because people are you can just use the network, and they're not pricing that. They're pricing that at a much lower price per bit than for text messaging or for phone conversations.
Sure.
And I think, and some operators are being much more aggressive in trying to sell that, to try and grab market share. So selling it at even lower cost.
But low-cost bits isn't the problem. Low-cost bits.
Yep.
The reality is, if we want to really reduce energy consumption, should people stay home? And I'm actually serious. People want to drive less and travel less and fill up more, and maybe really you start saving up big counts of cars and people around it. That's really a saving.
Yeah, exactly. I mean, the cost of a bit per CO2 per microgram, right, is nothing compared to the cost of moving meat for 10 miles to work every day, right?
I mean, many companies have gone to the model.
Yeah, but I'm just saying that all this kind of discussion we're doing is the energy costs of the bit is the problem. It's kind of ignoring the big picture.
The reason for this bike to work being big,
Right.
But on the other hand, if everybody comes to the office, the 20 tube lights are giving enough light to everyone, and then maybe all those people go to their homes, and then there are some tube lights getting over to them, so giving the light to them.
You drove your 2,000 car and back.
Yes.
Yeah.
No, the point is, yeah.
So I have some really good game theory ideas. So I'm looking for models. So the idea is, I think these things are hard to model. So how do you come up with models for these things, right? In terms of sort of.
I mean, if you simplify a lot of things, you throw away a lot of techniques.
Not seeing the big picture.
No, but I mean, if you are, you can fairly easily model. I think the missing part is the technology is very easy to model. Right? I mean, you can throw in numbers. You can play games where, okay, if I improve efficiency of power amplifier or so, this is the overall impact. Right? But then when you throw in the usage model,
Yeah.
that's
That's
the tricky.
All right.
okay.